Hello YouTube, RJ. Well, this is the fifth installment of our video on our V-7A HEATHKIT volt to voltmeter. It was a restoration where we completely restored the meter. If you haven't caught the series, I recommend you go catch it. Hopefully you'll find it interesting. But I thought that maybe some of my viewers might be interested in the more technical end of it, not just restoring, but maybe how does this circuit work? It's kind of an interesting circuit. It was used in a lot of meters because it was very practical and kind of ingenious, really. I thought in this video we would simply take the schematic, break it apart, and go through step by step exactly what happens in this meter that makes it work. First thing I thought we would do is start out by taking a look at the full schematic and showing you how I plan to do this. So let's take a look at the schematic. So here's our full schematic of the unit. And as you can see, due to linking all these switches and stuff together, it can be a little confusing. And I thought it might be a little more difficult to walk through explaining intermixed with the switches and such. So here's what I did. If you'll bear with me just a minute, I've made up a number of different things. For one, I broke the circuits down into their different sections. If you'll bear with me, I broke them down into a power supply, the bridge circuit, the AC rectification circuit, and then the range circuit. So what I'm going to do is I'm going to bring up one circuit and we're going to work our way till we understand the circuit, and then we'll look at how they link together. If you've noticed, I've cleaned up and removed switches and stuff off the diagram to get rid of clutter. So with that in mind, let's start with our first circuit. Let's get going with where I always like to start. It's a power supply. So let's go get onto the power supply. And this is the power supply for our meter. You can see here we have 120 volts. In my case, in the US, you had 120 volts coming in. And on the back of one of the switches, I did leave this part of the switch on, was a contactor that actually, when you turned it on anything but off, contacted these contacts and applied that 120 volts through the primary coil of the single transformer in the meter. Now what we got out of that was two different secondaries. One was a 6.3, and then this was another 120 volt winding. So the 6.3 is pretty simple. You get 5 to 6 volts AC out. These are filaments in the tube. There's two filament contacts in the 12AU7 tube. There's one in the 6AL5. It's important to understand a 12AU7 tube is really two triodes. So you really have two filaments in there. A single filament in your 6AL5 rectifier tube, and then it powered your pilot lamp, your light that lit up your screen and the display and lets you see that it's on, and illuminated the meter itself. From that 120 volts coming out, so you can see that we rectified that with a selenium rectifier, or a diode if you replaced it, on one leg of the transformer to get our positive side. And this gained us anywhere from 50 to 70 volts positive, depending on line voltage and such. On the opposite side, we tied in the 16 microfarad capacitor, 150 volts, but when you measure this, you're going to find out you easily get 160 volts on this. So I would recommend, if you change this, do a higher. I think I put a 250 in mine, but I would recommend a higher working voltage than 150 on that capacitor. Purpose of the capacitor is because you have pulsing half-wave rectified DC coming out of here, and we want to smooth it into smooth DC. So that's what this capacitor is doing for us. Now, as we move up the circuit, these two legs tie together through a set of resistors. Now, one of the resistors in the middle here is a potentiometer that we'll get into later on another circuit, how it ties in. But for the moment, what we're dealing with only sees it as, since it's not coming off the center tap, it's seeing a 27K resistor, a 10K resistor, a 10K resistor, and then right here a 100 ohm to ground. I need to explain this ground. This is not connecting the resistor to ground. This is creating the ground. This is creating a virtual ground. It's not the same as, a neutral coming off the hot line. This is your electronic ground reference that everything's going to reference inside this meter. Now, why are we doing this? Well, what it's doing is you've got positive voltage coming out here around 160 volts. But the developers, to run the tubes, needed negative voltage. So what they did is they went in here and put some resistors and dropped to a new created a ground, if you will, on the system right here through this 100 ohm resistor. And because it's in between these dividers of resistors, the potential of this is lower than this and higher than this leg. So if you can see where we're going, we're creating a negative voltage here and a positive voltage here. Now, working with tubes, obviously we need both positive and negative voltages. So this is how the power supply is creating that. So from this point on, you have to remember that your grounds are referenced here to this point. So they're not referenced to 120 volts here, nor here. They're referenced. You're not referenced here, you're not referenced here, you're referenced here. That gives us the negative on this side, the positive on this side. You end up with, 60 volts negative here or so, 40, 50 volts positive here. And we're going to use these voltages, as you see in a few minutes, in the meter. So our negative voltage runs off through this leg, and they go up into the bridge. The positive goes off into the bridge too, and we're going to bring that up and show you where these voltages are headed and what we're doing with them. So let me swap this picture out and bring up our next one. This is the heart of the meter. This is the clever part that makes it work. Everything this meter does requires this. This is really the heart of the meter. All of the rest of it is to meet the requirements of this circuit to make it work. So this is what we call the bridge. And what we have is our positive 50 to 60 volts that we come up off the power supply coming over here and tied to both plates on the 12AU7. So they're held at a steady positive voltage. Down here, right here, coming into the middle of this arrangement here, is our negative voltage we created off our virtual ground. That's 80, 85 volts, something like that, right here. Now, for the moment, I want to forget this resistor and this resistor. Imagine that they're not there. We're going to talk about it without them, and then I'm going to come back and explain where they come in. What you have here is you've got negative voltage running up to the cathode on each side of this tube. Remember, think of it as two tubes. It's two triodes in one tube, but it basically acts as two tubes. So what we do is we apply the positive to both plates. We apply one leg here to one cathode and the other leg to the other cathode. And what we have here is a tube that current will flow through depending on what the input to the grid is on each side. Current will flow through and cause a voltage drop across this resistor. The current that flows through, depending on how much current, generates a different voltage on this leg. How much current's flowing here will control the voltage flowing on the leg here due to this resistor. That in turn ties, and the only switch we're going to really use in the circuit description here is this one. I kind of need this one because I need to explain how the meter gets back and forth. Basically, depending on what range you're on, the input to this meter is changed to these different pots. We're going to talk about DC at the moment. So for DC, this switch brings one leg on this side into the meter. The other center tap off the DC calibration pot picks up off this leg, brings it into the meter. And why wouldn't you just hook it to one leg and the other? Is because you have the ability to reverse polarity on this thing. You've got the ability to go DC positive, DC negative, and you need to flip the meter connection, so this switch does this for us. Also, when we're doing AC, your adjustment controls are going to be different depending on if you're on DC or AC or ohms. So this switch also picks up one leg of the meter from one of these pots. When we're in DC, it picks it up right here and routes it through the switch over to the positive. The other side comes down directly in, routes around to the negative side of the pot. And by doing that, the meter can be switched polarity wise. The meter can be switched into series with different adjustments. So we can calibrate our DC here, we can calibrate our AC here, we can calibrate our ohms here, and they don't affect each other. And by what range we choose, what mode we select, we shift in the right calibration right here. That's the purpose of it. So hopefully I've made that clear what's going on right here with this switch, the meter, and here. So we've got these two legs. And as long as these two legs are producing the same voltage, it's going to be brought in by this switch to one leg or the other of the meter. And as long as they're both the same, no differential voltage will be here. Therefore, no current will flow. If this is at 40 volts and this is at 40 volts, you have 0 volts of differential. You have no current to flow. If no current flows through this meter, it's going to read 0. So what this is it's a balance beam, if you will. Basically, when you unbalance it, you get a differential here and the meter moves. So how do we get that differential? Well, if you look at this side of the tube here, you'll notice a 10 meg resistor and a capacitor tied to ground, going up connected to the plate. So basically what that creates is this plate will never change. It will be at your reference all the time through a 10 meg resistor. So by holding this, at some potential, fixed potential through this, a certain amount of current is going to flow compared to the voltage coming in here. So a certain amount of current is always going to flow. It's not going to change. Nothing we do when this meter is operational and up to temperature is going to change this current flow. So we have a fixed voltage here. Then what we do is over here, we have the same setup. We have a certain amount of current coming through, but that current is controlled by us. It depends on the input to this 3.3 meg resistor, what this grid does. If it happens to be exactly matching this at this point, you would think the meter would center, but it won't. If you have the same potential here as you have here, the meter is going to slam one way. Why is that? Because if you look down here, you will notice that these two resistors are not the same. One's 150 and one's 220. Now, you would think you'd want these to be the same, and that would make sense. But the designers came into a little bit of a challenge. If you think about this circuit, if you're into oscillators and stuff, you realize that because if you had the exact same current flow through here, you would get an instability, which would cause any slight variation of flow to change the flow on the other side because they're tied to the same supply. And what could happen is you could get oscillation where these two sides of the tube start oscillating back and forth. That wouldn't be good. So to prevent that, instead of having it perfectly balanced, they use a different resistor on one leg and they unbalance the circuit naturally. So once you unbalance the circuit here where they don't flow the same amount of current at the same potential, the oscillation doesn't happen. Because of that, you don't have the same flow of current, the same voltage from the same current. Therefore, you're going to get an offset. And so how we fix this is where these two resistors come in. We place a path between them with a 10K pot. So what we do is put a 150K resistor on the wiper of this pot. And depending on how you adjust this pot, you're kind of putting your finger on the scale one way or the other, if you would. You're forcing it to swing one way or the other. You're affecting the current in these legs. This is your zero adjust pot. This is how you balance it. You balance it with this to get the meter to read 0. So this section right here is the very important part of the system. So when you zero it and get equal here and here with your probes ground, you're basically calibrating it so that when the probe's touching and there's no voltage differential, this side and this side applies what is needed to get the same voltage. It won't be the same current because the resistors are different, but you make up for it here by imbalancing the system here to make it neutralize the needle to 0. Now, once that's happened, now you have this very sensitive teeter-totter balance that's perfectly balanced. Even the slightest little bit of adjustment on one side or the other will make the balance swing and cause the needle to swing. What we end up with here is a scaled down version of the voltages that we're looking at in DC mode. And any applied voltage here will increase the current flow and cause the meter to displace. It's going to raise the voltage on this side, not raise the voltage on this side. They no longer are going to match, and the needles are going to move in representation of the voltages that are being put in here. This is the main part of the meter. This is what makes the meter work. It's quite clever if you think about it. One thing you can run into is if your tube is not fairly well balanced here, what will happen is it will require quite a bit of adjustment of the zero to one side or the other. Theoretically, if your tube's bad enough out of balance, you could end up where you max out your zero adjustment, you can't balance it. But it takes quite a bit of being out of balance. A good tube that's very close in balance, this thing will pretty well balance dead center if your resistors are accurate. As the years go by and these vary quite dramatically, it starts requiring more and more variation of the pot to keep you balanced. That's what you're doing when you're zeroing each time you change scale and you zero your meter, what you're doing is you're changing this pot and you're rebalancing this teeter-totter balance to get it perfect. Now, based on that, we have to discuss now. We know where our negative voltage comes in. We know where our positive voltage comes from. We understand where we get our grid control here. It's just connected to ground through a resistor. But one more thing. These capacitors, if they start leaking, you could see how that might cause problems because you've got a pretty high resistance here. But if you start leaking through this capacitor, you're affecting that, and you're going to change how much current flows on this side. Over here, if you start leaking, the voltages you apply, some of them will leak, and therefore you really won't get on the grid what you should. So these capacitors can cause you problems. Let's jump on to the next circuit. The next circuit that we're going to talk about is the scaling circuit. How do we end up with a voltage on the grid of the tube to tell us how much voltage we're getting? Well, it's pretty straightforward, really. You've got a bunch of switches up here that I'm not going to get into with, but basically they're just deciding what to do with the incoming probes, which probe's coming in, where it should be routed to make sure it goes to the right place. For example, the AC signal you don't bring to this resistor array. You go through a rectifier first. So it needs to route that to the rectifier before it comes here. On the other hand, when the DC comes in, it routes it straight into this. So those switches, as complicated as they look, that's what they're doing. They're deciding, do I send it to the rectifier first? Do I send it to the resistor tree first? The resistor array first? Do I send it to, is it ohms? And I'm going to go over and use the other one. These are the things. Is it negative DC instead of positive DC? And I'm going to flip that switch in the bridge to make sure that our meter reads correctly. That's what they're doing. They look complicated because there's multiple switches in one switch, but that's all that's going on with the system. So here what you have to think about is your DC probe comes in, goes to a switch and gets told, okay, this is DC, just send it right here. So whatever voltage you apply in DC comes here to this point. Now, if your range is set to 1.5 volts, your lowest range, that voltage directly routes past all these resistors and straight in through here, and that goes up to the 3.3 meg resistor on the balance circuit, on the bridge circuit. Now, that doesn't mean these resistors do not matter at that point, because if you notice, they're hooked to our reference ground and they're still wired into this. So they're still a factor. You still need to understand you have this here. Now, what is this? Well, it's 7 megs and 2 megs, 700K, 200K, 70K, 20K, 10K. What do you get if you add those up? What if I told you if you add those up, you will quickly realize that you add these up, what do you end up with? And why is it the way it is? Well, let's go over here and look a second. Jump back to the bridge. How many mega ohms do you have from ground to this plate? To this grid, I mean. 10, right? Okay. You've got 3.3 to this one. Okay. So what happens if we come over here and add all this together? What you're doing is you're creating a balancing resistor to ground to offset the other grid side of the tube. So these resistors are always in line with that grid. But what happens is when you bring DC in, if you're looking at the 1.5 volt scale, it doesn't reduce the voltage that you're reading. It goes to the tube. So this ends up going through the 3.3 to the tube, and then the tube reacts by increasing its current flow comparative to what you're putting in and makes the meter move, and that's how you read a voltage. Now imagine you want to read higher voltages. Well, if the meter will peg out with 1.5 volts put in on this circuit, you sure couldn't put 150 volts in there. So we have a range selector. And what it does is every time you go up to a higher voltage range, you require your voltage from your probe to go through resistors in this array, which are basically, if you look at it, you realize they're a resistor divider network. So each time you make it go through more of them, you get less and less voltage. So when you switch to say 15 volts from the 1.5 volts, that same 15 volts here, by the time it gets to here to come out and go on its merry way, it's only 1.5 volts. And so each time you go up, you cause your input voltage to be dropped to a multiple matching the range, and therefore that same 1.5 maximum voltage, 0 to 1.5, will come out and affect the meter. So this is where the magic of taking different readings of different values comes right here. That's what it does. Now over here you see another set of resistors in a very similar setup off the same range switch, but there's a battery in series down here. This is your ohm meter. It does the same thing. As you choose the switch, you also choose these in. And depending on where your mode switch up here is, whether it's on ohms or not, the voltage will be routed into here and then back through to the meter. And it does the same thing. It scales by putting resistors in line series with your resistor you're measuring. And because if we know this resistor and we know how much voltage is going through these resistors, and then across the resistor that's unknown you're measuring, the voltage coming out will be relative to that with Ohm's law. So you will get a reading matching ohms. So that's all that's happening over here. It's a very straightforward setup. So this is how you scale. This is how you control how much voltage. You take every voltage you input in this thing on DC and you scale it to 1.5 volts. 0 to 1.5 volts. If it's 15 volts, it's scaled by a factor of 10 and you get 1.5 out at 15 volts. If you go to the 50 scale, if it's 50 volts, it'll be scaled to 1.5 volts to max the meter out and it'll send it on its way. So that's how the scaling works. So let's bail out of those and let's get into the AC side of things. The AC has one more problem. The AC meter is just a DC meter, but you can't really measure AC this way. So what you do is you just convert it to DC. Easy enough. We just rectify our AC input into DC, and that's where this 6AL5 rectifier tube comes in. Your probe is hooked up for AC, and you're on AC mode. Whatever voltage you put on the probe comes up this leg through this capacitor, which filters as a blocking capacitor for coupling. It'll just knock any DC off and give you just the clean AC signal. The AC signal comes up and they have right here another array of resistors that think of them as a pre-scale. And this is the same range switch down there, just another wafer on it. And what happens is if you go up to 150 volts, it doesn't pre-scale. But when you start trying to use the 500 or the 1500 volt scale, you need to knock the voltage down even more. So what happens is it uses this to pre-scale the value down ahead of time. Whatever comes through, if it's 1.5 volts, it'd be right here. If it's 1500, it's going to come through these resistors, be dropped down and come in. It goes through another blocking coupling capacitor, and it's applied to the plates. Well, it's applied to the cathode of one side and the plate of the other. And what this does for us is whatever comes in as AC here is going to come out as DC here. This then gets regulated back down through, it's not regulated, it gets routed back down to our meter system to go over and be put on the bridge to measure it. So all you're doing is adding a rectification, sometimes pre-scaling on the high volts, but rectification to get you back to DC to measure. Now, where this line runs here is, we're going to go to the full schematic to look at that. I'm going to bring the full schematic over and we're going to talk about that last part of the circuit. Okay. So what happens here is, when this comes out, it goes down and it gets run through our resistor array to scale. So it gets scaled after it's turned to DC, right? Can't run the AC into the resistor bridge. So what happens is, it gets converted to DC, routed back down through, and we go through the same thing the DC did. It works exactly. The DC, it's a DC meter that we happen to be able to rectify AC into DC to measure. But a problem you run into on this rectifier is that whenever this rectifier is operating, it's going to build up some electrons in it. And what's going to happen is, you're going to have a little bit of a current, or potential, I should say, here, that's manufactured from the operation of the tube. It's not going to have anything to do with your AC. It's going to be there all the time. So what we do is, we have these 22 meg resistors across here that come over, comes down, goes back to our power supply side. And this is that potentiometer that we were ignoring as a potentiometer in the power supply. We were just looking at it as a through resistor. There's a potentiometer right here, and what this does is allows us to tip the potential of this line one way or another, positive or negative. And so one of the calibrations is to do an AC balance. And what that does is, whatever amount of potential you generate here when you're not putting an input in, you null out, you get rid of by adjusting this pot. So it does away with that, brings it to zero, so that all we get is just our input potential coming back. And you wouldn't be getting a zero. So basically, this is kind of the AC zero. It's similar to this DC zero adjust, but for AC. It gets rid of any stray potential here. And really, we've just covered the circuit. If I go out and look at it, all we really didn't get into is how the switches route around and around, but that's just, you could follow the switches out and figure that out. There's nothing more than switches routing whether we're using this circuit. Is the potential going in here going to be read as a positive or a negative voltage? Is, that's really what's going on. What range, either voltage range or ohms range, are we scaling on? Now here's your battery. If you put a battery limiter, you're just getting rid of that and putting a circuit in to apply the 1.5 volt in here. So that's it. I hope my explanation was halfway clear. I hope it was helpful, and I hope you learned something from it. I was endeavoring to break this down to the simplest little circuits and show that it's a very simple circuit, but it's quite clever. It works very well. This unit can perceive such slight voltage differences because of you're taking that tube and you are balancing it so finely that it can sense very, very little change. The other benefit, of course, with the vacuum tube voltmeter, the big thing this brought us, and the reason vacuum tube voltmeters exist, is extremely high input impedance, around 11 mega ohm input impedance. That was fantastic for their day when they came out. Common meters were usually 20,000 ohms a volt, and so they loaded the circuits. Thanks for tuning in. Hope to catch you in another video. Hopefully you enjoyed this. Let me know if you like this technical talk, or whether you prefer me renovating equipment, or let me know what you like so I know what to tune the channel for. And if you haven't subscribed, do me a favor, subscribe, help the channel grow a little bit. Hit the like button if you like the content, and hit the notify bell so you get told when I put a new video out. See ya.